Welcome to my presentation on the design and implementation of a stopwatch-style counter using an FPGA. So, what is an FPGA? FPGA stands for Field-programmable Gate Array. Essentially, they are complex digital devices designed to be configured after manufacture. Hence, field-programmable. They are mainly used in the development of ASICs, application-specific integrated circuits. ASICs can be found in just about all modern digital electronic devices. So why are FPGA so widely used? FPGA offer many attractive features, but the most beneficial are performance, time to market, cost, and reliability. Parallel hardware allows for much more computing power over sequential execution. FPGA technology offers flexibility and rapid prototyping capabilities. FPGA circuitry is truly a hard implementation of program execution. The FPGA used in this project is the Xilinx Spartan3E-100. Spartan3E is the family and 100 indicates that it has 100,000 gates. Although no longer in production, the Spartan3E offers an affordable entry-level solution to getting started with FPGA. The development board used in this instance is Digilent's Basis 2. Development boards offer a variety of inputs, outputs and connectors to aid in the development of systems. Digilent offers Adept, a software solution used to write the configuration files to the Spartan3E. Now that we have briefly discussed the basics, let's take a look at the stopwatch-styled counter. Shown is a block diagram of the structure used in this implementation. As shown, there are four main components: a clock divider, multiplexer, decoders and a 16-bit counter. The clock divider drops the 50 MHz reference clock to usable frequencies. These frequencies are used for the counter, multiplexer and anode decoder. The core of the design is the counter. All other components are needed to display the count on the 7-segment displays. Let's take a look at the control operation. As shown, the stopwatch control is provided via 3 push buttons. Button 0 toggles between start and stop. Button 1 resets the count. Button 2 changes the direction of the counter. Let's demonstrate this counter in action. This is the counter on startup. All digits display 0 as the counter waits for the start signal input. Button 0 is pressed, starting the counter. The counter default is to count up. Button 0 is pressed again to stop the counter. Button 2 is pressed to change direction of the count followed by start. The counter now counts down. When reaching 0, the counter will roll over to max count and continue counting down. Stop-start functions as usual. Button 1 is pressed to reset counter to 0. There are two important things to note. The first is the speed of the counter. Due to the configuration of the clock divider, a frequency of 0.75 Hz instead of 1 Hz results in slower counting. The second is the length of the button presses. The code uses a polling read method. This method works fine for high frequency applications. However, due to the low counter frequency, button presses need to be held for over a second to ensure that they have been read correctly. Final thoughts of the project. These two issues would have to be resolved to consider it an outright success. However, the overall design worked well otherwise, and with some more time these issues could be resolved. This concludes the presentation. Thank you for your time. I hope you enjoyed the demonstration.